All right, so let's get started. So today is going to be the last class for the semester. And I think throughout the semester, we have looked into multiple new concepts. For example, we have looked into non-idealities in op-amps. We have tried to understand why those non-idealities in the op-amp exist. And the non-idealities in the op-amp goes back to the devices inside it. The device, which could be a diode, which could be a MOSFET, which could be a BJT, although we have focused mostly on MOSFET-based designs. But now you know that, okay, why my input impedance should be infinity or should not be infinity, in which conditions it may not be infinity. Let's say you are having an input frequency which is very high. And in your homework 6, you have seen that if your input frequency is high, the input capacitances may become a short or may become something that is toward a short. And in that case, the input impedance may not exactly be infinity at that frequency. You have seen that why output impedance may not be zero, because whichever implementation you have, like even if you have a source follower at the output impedance of the source follower is not zero. It's 1 upon GM of that source follower. And that is the reason why we see that for an op-amp, the output impedance may not exactly be zero. We have seen how to increase the gain of the op-amp. That is by cascading multiple stages of amplifiers. So you can have a single stage amplifiers, but you can cascade multiple stages to increase the gain. And then we have seen that we run into a problem that there are too many poles in the system. You want a single pole for an op-amp because of a few different reasons. First of all, you do not want instability or oscillations because of the op-amp. And secondly, of course, you want your analysis to be simple. So that is why you want your gain bandwidth product to remain constant at whatever gain and whatever bandwidth you have for the open and closed loop systems. Only if your gain bandwidth product remains constant, then the open loop gain multiplied with the open loop bandwidth will be same as the closed loop gain multiplied with the closed loop bandwidth, and the gain bandwidth product as well as the unity gain frequency, they will be same. Right. So because of all of that, we want to have a simpler system, and that's why we want to have a single pole system. And you have also seen how to do that. And at the very end, we have started looking into some of the digital circuit requirements. We'll continue with that discussion today and try to finish it. One thing that we did not discuss or we could not discuss in the class is BJTs. However, I have uploaded the lectures, recorded lectures, as well as the material for BJT, so that you can always go back and maybe learn about BJTs a little bit. In many ways, you'll see BJTs and MOSFETs will be very similar. I'll suggest that before if you are going for an interview to Analog Devices or TI or any other analog circuit design profile, please look into BJTs as well and go over those recorded lectures. Okay. One of the announcement is that your final exam is next week, December 10th, 3 to 5 p.m. in this room. I have uploaded some of the important topics and some practice problems. So please go over those practice problems as well before the exam. But homeworks 4 to 9, that is when we started discussing about DC biasing of amplifiers to all the way up to op-amps and then digital circuits. Please make sure that you go over those homeworks again before and just recapitulate all the concepts before you come prepared for the exam. Exam will be in person during, sorry, I'll just update this. So it's not during class hours, it's at 3 to 5 p.m. Right? Now you can use the class notes or books. This is an open book, open notes, and open digital device exam. So you can make use of all the class notes or some of the notes that you have made yourself. Syllabus, again, anything related to homeworks 4 to 9, maximum marks 100, time would be 2 hours, 3 to 5 p.m. But I'll prepare the question paper in a way that if you know what you're doing, you should be done within an hour, right? So it will not be a lengthy exam, but you have to use the concepts that you have learned in the class. Please bring your calculators because your calculators may be required, and I think it will be required for some of the calculations that you'll need to do. And of course, good luck. And I know all of you will do very well. So that's for next week. Today, we're going to finish our discussions on digital circuits. But before I go there, I just need to set up my laptop because I think there's some technical difficulties here. In the meantime, I'm seeing that in Getter evals, that's only about 10 to 20% of submissions. So I'll try to set up my laptop within the next 2 to 3 minutes. In the meantime, could you please go ahead and submit some of the evaluations if you haven't already done so?
So, hi, Professor. Can I have a quick question?
Yes, please go ahead.
Okay, I have just a quick question about the homework solution 8 and 9. I know that the homework 9 is gonna be due on the December 10th, same day at the exam. So, and I just wonder when the solution of the homework 8 and 9
So
can be
homework
uploaded.
8 I'll post today after the class. Homework 9 also I'm because I want you guys to learn about how to solve these problems. We'll
Mhm.
actually discuss about homework 9 problems during today's class and how to solve them.
Okay. And how about
Okay.
homework 8?
Homework 8, we have already gone through the process of how to solve homework 8,
Okay.
and I'll upload the solution today.
All right. I got it. All right. Thank you very much.
Yeah. But I may not get enough time to go over both the solutions of homework 8 and homework 9 today. But homework 8, the process, I have already gone through that in the class. And the
Mhm.
way it has been solved, it's exactly the same.
Okay. I got you. Thank you.
Oh, all right. All right. So let's get started. Um, So today we are going to look at how we design digital logic circuits. And by digital, we mean CMOS logic circuits, where we're going to use both NMOS and PMOS transistors. As we have seen in the last lecture, that generally NMOS transistors constitute the bottom part of the CMOS circuit, and PMOS transistors constitute the top part of the CMOS circuit. The bottom part is called the pull-down network, or PDN. So the job of the bottom part of the circuit is to pull down the output level, which let's say originally at a digital 1 or a logic level 1. The job of the pull down circuit or the pull down network is to bring down the level of the output to a digital 0. On the other hand, you have a pull up network, which is constituting of these PMOSs. And the job of the pull up network is to pull up the VDD by charging this output capacitor. Um, so your output capacitor will be pulled up to the VDD level or the logic high level using the pull-up network whenever the pull-up network is on. Now, how do we design logic circuit with this pull-up and pull-down network? We have also seen Why we are going to use PMOS in the pull-up network? That's because PMOS is a good conductor of digital ones. If you had used NMOSes, the NMOS will charge up only up to VDD minus VTH, because after that, the NMOS devices will turn off. On the other hand, why do we use NMOS devices in the pull-down network? That is because NMOS devices are better at being used as a discharging switch, or they are good in terms of when you're trying to conduct a digital zero. If you had used a PMOS-based pull-down network, what would have happened is that the capacitor will only discharge to the threshold voltage level and not to the zero level. Right? So you may use a PMOS in the bottom or NMOS at the top, but then that circuit will not be efficient. And that is the reason why PMOSes are used at the top, NMOSes are used at the bottom of any CMOS circuit. So how to design these kind of CMOS circuits? Let's take an example of NOR, or a negative OR. Negative OR means it's just the opposite of OR gates, right? For OR gates, if one of the two inputs is equal to 1, the output is supposed to be 1. So any one of the input is equal to 1, the output is supposed to be 1 for an OR gate. But for a negative OR gate or a NOR gate, it's exactly the opposite. So only if both the inputs are 0, the output is equal to 1. In all other scenarios, the output is equal to 0. So how do you implement this? So what it says is that if any of the input is equal to a digital 1, discharge the output to 0. Now that directly gives you an intuition that, okay, if I can turn on my switches and make, please keep in mind that in this case, for any digital circuits, the transistors will be used as switches. They are not being used as amplifiers anymore. In analog circuit, you want them to be used as amplifier and you want them in the saturation region. In digital circuit, you want to be used as switches. So either the switch needs to be off, and in that case, the impedance across the transistor will be very high, the switch is off, or you want the switch to be on. And in that case, the impedance across the transistor needs to be very small, because an ideal switch, when it is on, has 0 resistance, and when it is off, has infinite resistance. So you want your transistor to operate in the triode region when the transistor is on or the switch is on, or you want your transistor to operate in the cutoff region when the switch is off. You do not want the saturation region, which is somewhere in between, right? So you want the transistor to be fully on or fully off. That is, you are interested in the triode and cutoff regions, and you're not interested in the saturation region, which is the biggest difference with any analog circuit design. Okay, so now you have these switches, and if any of these switches is being on, the output capacitor is going to be discharged, right? So how to implement that? If you put the switches in parallel, let's say I have a switch which turns on when A is high, or I have a switch that turns on when B is high. So I have a transistor which turns on when B is high. I also have a transistor which turns on when A is high. Now, if you put them in parallel, that means that if either of them is high, if either A is a digital 1 or B is the digital 1, that corresponding transistor or that corresponding switch is going to be on. And in that case, the output or the output capacitor is going to get discharged through either one of those switches. And when both of them are on, of course, it will get discharged through both of them. So the easiest way to implement a CMOS circuit is to first look at the condition when the output is going to get discharged, okay? And then implement your NMOS network with that. Now, how do you construct the PMOS network or the pull-up network? Because PMOS and NMOSes are dual of each other, wherever you had parallel combinations will now become series combination. Wherever you have series combinations will now become parallel combinations. So because for the pull-down network for NOR gate, you had A and B both were in these transistors were in parallel. So the pull-up network transistors will be in series. And how do you know that that is true? Or that is what you want? When do you want the output capacitor to be charged or pulled up? There is only one scenario when you want that, when both of the inputs are 0, right? So when both of the inputs are 0, you know that the PMOS turns on. PMOS is the dual of the NMOS. The PMOS turns on when the input is 0. The NMOS turns on when the input is 1, right? And why does the PMOS turn on when the input is 0? Think about this PMOS on the top. The source is at VDD. The gate is at 0. And in that case, the VSG will be positive or VGS will be negative. And that is the condition when the PMOS will turn on, right? So only if your input is 0 and your source is at a high voltage, then the PMOS turns on. Now you want both your PMOSes to be on at the same time. Only then your output is going to be charged. And the way to implement that is to have both of them in series, because only in that case, if both of them are 0, then both the transistors or both the switches are on for the PMOS. And then through this path, your capacitor gets charged. Right? Now you can, like that is basically the intuition or the understanding that you need to develop, that why my PMOS devices are in series when my NMOS devices are in parallel. But if you have already implemented the pull down network, you can just like to implement the full CMOS circuit, you can just remember that, okay, whatever is parallel, whatever is in parallel in the pull down network will be in series in the pull up network, or whatever is in series in the pull down network will be in parallel for the pull up network. And the reasoning is something that you can just think about it and you'll understand. Similarly, if you want to do a NAND gate, it's negative AND, which means that if both of my inputs are 1, my output should be 0. It's negative of AND. AND is when both of my inputs are 1, my output is 1. When in all other cases, my output should be 0. Negative AND is just the opposite of that. So you have this truth table on the right. How do you implement this? When do you want 0? When both of my inputs are equal to 1. How do I implement that? I have both of my inputs in the pull down network in series, because only if both of them are 1, then my output gets discharged. In all other cases, my output stays charged. So if my pull down network, the transistors are in series, in my pull up network, the transistors will be in parallel. Also, you can think of it in this way, that if any of these pull up network transistors are on, if A transistor is on or the transistor connected to B is on, right? You are going to charge. So let's say the transistor corresponding to A that is on. So the output will charge up through this path. If the transistor corresponding to B is on, the output will charge up through this path. If both of them are on, then both of them will charge up the output, which is the condition of 0, 0. And remember that PMOS is on when the input is 0, NMOS is on when the input is 1. Again, something that we have learned before. All right, so that's how you implement NAND gate. How do you implement any arbitrary logic? So let's say I have a logic which says that I want my output to be A ANDed with B or C, and then everything needs to be complemented. So A ANDed with B or C, and then a complement of the entire thing. Of course, you can write down the truth table and find out where your zeros are occurring. And then corresponding to that, you can create your pull down network. Your pull up network will be a dual of that. But there is an easier way. The easier way is that your output is this. Let's say Y is denoted by my output, which is A ANDed with B or C whole bar. So that's my output. So let me write that here. So this is my output Y. Now, if I want to create my pull down network, I'm interested in when my output discharges. So I'm not interested in when my output becomes 1. Rather, I'm interested in when my output becomes 0. So I'm interested when I'm trying to create the pull down network, which will discharge the output. I'm interested in Y bar. I'm not interested in Y, right? I want to discharge the output. So Y bar is what? Y bar is going to be A ANDed with B or C. Now without looking at the truth table, you can actually create the pull down network. That your Y bar is going to be A ANDed with B or C. What does OR mean? That any of the paths can be on. It's OR, either or. So your B or C, these transistors are in parallel. And when you created this parallel set of transistors corresponding to B and C, you connect your transistor for which the gate is connected to A, and then keep it in series because it's A ANDed with B or C. So A needs to be high and B or C also needs to be high so that your Y bar is high. So now that you have created your pull down network, which is A in series with B in parallel with C. So that's your pull down network. Your pull up network is going to be the dual. So your B and the transistor corresponding to B and the transistor corresponding to C, they are in parallel. Now they will go in series. And the transistor which was corresponding to A, that was in series with this entire combination of B or C in the pull down network. So in the pop network, that will be in parallel. So it's just a dual network for the pull down. Question. What do you mean by using separate smaller gates and combining them?
The circuit up for exact equation.
Okay. So I got your point. So you're asking that why don't I use a OR gate? Why don't I use an AND gate? And then why don't I use an inverter? So what you're saying is that I'll use an OR gate first and connect B, C to that, right? And then I want to use an AND gate. That means I will have A, and then after that, I'll connect an inverter, which will be my final output, let's say Y. Exactly. So NAND gate is an universal gate, NOR gate is an universal gate. So you can use De Morgan's theorem and convert them into universal gates, right? But now you have asked a very, very important question, that what's the advantage of this? Okay. So remember that here on the right-hand side, this is perfectly fine. You have implemented a digital logic, what you're saying. But you have used one OR gate, one AND gate, and one inverter. How many transistors do you need to create an OR gate? We have just created an OR gate a little while ago, right? So you have created an OR gate, which required 4 transistors. And then if you want an OR gate, right? Not a negative OR gate. So you need to invert this output. So 4 plus 2 transistors for an inverter, 6. So just for the OR gate, you need 6 transistors. Now think about how many transistors we need for the AND gate. Again, you have 4 for the NAND gate, and then you need another 2 for the inverter. So basically you have 6 over here. And then you may say that, okay, instead of using, if you use another inverter, you'll need another 2. So you need 6 plus 6 plus 2, 12 or 14 transistors. Now you might argue that I'll combine this AND gate at the end with the AND gate so that I have only a NAND gate. So I can just create a NAND gate and then get rid of the inverter at the end, right? So in that case, the NAND gate will require 4 transistors. So that is 4. So still you require 6 plus 4, that is 10 transistors. Okay. Now, how many transistors you required here? 1, 2, 3, 4, 5, 6. So you have implemented the same thing with just 6 transistors. Instead of 10 transistors if you do this implementation, and 14 transistors if you use a OR AND followed by an inverter. And in circuit design, the more transistors you use, that is real estate, basically. The more transistors you use, you're using up area. And area is real estate in circuit design. So if you can use less number of transistors, it's always useful, more useful, because less area, less power consumption, you can do other things, have other functionalities in the area that you have saved and so on. So that is the biggest advantage of implementing the entire logic using CMOS instead of dividing it into smaller gate or let's say universal gates and then trying to implement them using universal gates. But very important question. Thanks for bringing that up. All right. So in your homework 9, basically the first problem is draw the schematic diagram with a standard CMOS logic to implement this. A or B ANDed with C, or with D, and then whole bar. So you should now know how to implement this because you have already seen how to implement this digital CMOS logic. So if you're trying to implement A or, so remember that this is your function that you want to implement. First thing to do is to implement the opposite of this because you want to, like NMOSes are easier to understand. At least to me, NMOSes are much easier to understand, right? So I always draw the pull down network first. And to draw the pull down network, you'll be interested in what is E bar, right? Because you are interested in when you discharge the output. So this particular digital logic means that this digital, the way you have to implement that when A plus B ANDed with C plus D whole bar is satisfied, the output is going to be equal to 1. But the NMOS's job is to make the output equal to 0. It's the job of the NMOS is to make the output discharge. So for the NMOS, you are interested in E bar. And E bar is just that this, the overall negative complement sign goes away. So you have A or B. So A or B, they are in parallel, ANDed with C, that's in series. And the whole thing is ORed with D. And D comes in. Okay. So that's your pull down network. What is going to be your pull up network? Exactly the dual of that. Since A and B, they were in parallel earlier, now they will be in series. Earlier, C was in series with the parallel combination of A and B. So C will be in parallel with the series combination of A and B. And finally, D was in parallel with the entire thing for the pull down network. So D will be in series with the entire thing for the pull up network. That's how we implement the CMOS logic. Okay. All right. So that's the first part. To solve the second part, let's again go back to our theory. So in terms of dynamic power, how much power you are going to consume? So for pull-up resistor, what the pull-up network is doing is that the pull-up network is charging up the capacitor at the output. Whatever pull-up network you design, that's charging up the output capacitor. And whatever pull-down network you design, that will be discharging the output capacitor. Now, these are switches. These are transistors being used as switches, but transistors are non-ideal switches, right? Ideal switches will have zero resistance or infinite resistance, depending on whether they are on or off. But non-ideal switches, which are transistors, they will not have zero resistance when they are on. They'll also not have infinite resistance when they are off. Correct? So R on and R off of the switches, they come into play and they determine how fast your output is going to be charged or how fast the output is going to be discharged. Because while charging, the resistance of these switches, on switches, will create an RC time constant. While discharging, the resistance of the on switches in the pull down network will create an RC time constant. So you'll have a RC time constant both during charging as well as during discharging. Because the transistors have resistances themselves. They are not ideal switches, right? They're not ideal switches, and that is the reason why you'll have these RC time constants. Also at the same time, they are basically charging up the capacitor or discharging the capacitor. You have already seen how to figure out the power consumption while you are charging or discharging a capacitor, right? So this is something we had discussed in the previous lecture, that as you are charging from, let's say, VDD using a switch and a capacitor, you're charging this capacitor, you have already seen how we did the integration, and the charging energy that you're drawing from VDD is CV squared. Out of that, half CV squared gets stored in the capacitor, half CV squared gets lost when you're charging. When you're discharging, that half CV squared energy that was originally stored in the capacitor, that is lost during discharging. So you lose half CV squared during charging, you lose half CV squared during discharging. And we figured out how to do that integration or that calculation in our last lecture. So that's about power consumption when you're charging or discharging a digital circuit. And for every charging or every discharging, you consume half CV squared amount of energy. How much is the power consumption? Of course, if energy, you know that energy is equal to power multiplied with time, right? That's the basic definition of energy, that you consume some amount of power over some time, and the multiplication of those two is the energy. So that means your power consumption is energy divided by time. Now, if your charging and discharging is happening in a cycle, right? Let's say it's happening alternatively. That's what happens, for example, in a clock, that you go up, the clock goes down. Again, clock goes up, clock goes down. So whenever you see a repetitive pattern, basically the time within which you have to charge and discharge is basically the time period of that signal. So this time t is the time period of the signal, which means 1/t is frequency. So power is equal to energy multiplied with frequency. Because you know that the charging energy is half CV squared, the discharging energy is half CV squared. So the power during charging or discharging is half CV squared times F. Now, this is something you may have heard in other classes or during other discussions, that for digital circuits, the power consumption is half CV squared F during each charging and discharging. And that's where the frequency F comes in, because energy is just power multiplied with time. Okay. But during the full cycle, your power consumption is CV squared F, not half CV squared F, because you have half CV squared energy during charging and half CV squared energy during discharging. Okay. So dynamic power in any digital circuit is FC VDD squared or CV squared times F. Okay. That's the formula for dynamic power in digital circuit. The other important consideration is the propagation delay. Now, propagation delay is we already talked about this, that because the transistors are not ideal switches, they have resistances. So there would be a RC time constant during charging, and there would be a RC time constant during discharging. It will not be instantaneous charging, and it will never be instantaneous discharging, right? So the charging and discharging curves will always look like that. Now, there are a few definitions of propagation delay. Again, that is a concept that might be known to some of you through other classes, but we are going to repeat that again. That propagation delay is usually defined in terms of 50% propagation of, or the time required to reach to the 50% of the full charging level. So if your full charging level is VDD, when do you reach VDD over 2 during charging? And when do you reach VDD over 2 during discharging? The distance between those 2 points is called the propagation delay. So that's basically the overall propagation delay from charging to discharging. You can also define the propagation delays during charging and during discharging. So those propagation delays are basically defined as tau propagation low to high, that when you're going from low level to a high level. Now that propagation delay could be from 0 to 50%. And during high to low transition, it could be 100% to 50%, right? So it could be defined in that way if you're interested in the 50% levels. There is another way to define propagation delay. Sometimes people use 10% to 90%. And why do they use 10% to 90%? Because there could always be noise near the ground, and there could be noise near the VDD. You have seen that in your measurements, that the VDD line or the ground line is always noisy. So if you don't want to discount, or if you don't want to encounter any kind of error because of that noise on your VDD or ground line, what sometimes people do is that they will consider only the 10% of the signal level to 90% of the signal level as the propagation time from low to high. And again, 90% of the signal level to 10% of the signal level as the propagation from high to low. Any of those things are fine, but you have to mention which one you are doing. Are you considering a 10% to 90% propagation? Are you considering a 20% to 80%? Because you might have more noisy scenarios and your signal levels could be smaller, then maybe 20 to 80% makes more sense. But you just need to mention that, okay, what is your assumption? Are you doing a 10 to 90% propagation? Are you doing a 20 to 80% propagation? Or are you looking at only to 50% to 50% levels, right? So as long as you mention that in your data sheet as you're building a circuit, you're fine, right? Just you need to mention what you are doing. Okay, now this propagation delay, let's say tau p, and in this case, let's just consider tau p of low to high and tau p of high to low. That is going to be an RC time constant. And usually, the value is going to be R on times C times ln2. And we'll just prove that in the next page, that why this ln2 is coming in. And that boils down to 0.69 times R on times C, because ln, or natural logarithm of 2, is equal to 0.69. Right. So basically, you'll see that the rise time and the fall time, that will also be defined in many books as just that 10% to 90% levels. So if you're talking about only the rise time, then you're talking about the 10% to 90%. So as you are rising from 10% signal level to 90% signal level, that's what is called the rise time. Again, if your signal is falling from the 90% level to the 10% level, that is called the fall time. And you can prove that rise time and fall time is equal to 2.2 times R on times C. So tau p, which is the propagation delay for the 50% times, that's basically 0.69 times R on C. And rise time and fall time of 10 to 90%, that is 2.2 times R on C. All right, so let's now see why that equation is true. So if you're thinking about RC time constant, let's say you have a resistance and then you're charging this capacitor. So the capacitor charging profile will look something like this on the right-hand side. And you know that tau, which is RC, is the time constant for that capacitor charging. What is the equation of the capacitor charging? That the output, which let's say VO as a function of time, is equal to VDD times 1 minus e to the power minus t over tau. Again, this is something you, I believe you have learned in 3111 or other classes, maybe even physics of EE, because there you learn about the capacitor charging and discharging equations. So this is the equation for capacitor charging. The maximum voltage times 1 minus e to the power minus t over tau, where tau is equal to R times C. Now, if you want to calculate the time to reach, let's say you want to reach voltage Vx, any voltage Vx, and for that, you need time Tx, and that x is unknown, of course. So you want to reach to voltage Vx in time Tx from voltage V0 at time t equal to 0. So your Vx over VDD, the Vx over VDD, if your output, the target output voltage is Vx, so Vx over VDD is going to be 1 minus e to the power minus Tx over tau. So e to the power minus Tx over tau is going to be 1 minus x, where x is the ratio of Vx and VDD. So Tx is going to be tau times ln of 1 minus x. Now you can put whatever value of x that you want. Let's say you want x to be equal to half, right? If you want to reach 50% of the overall voltage, right? Let's say you want to reach VDD over 2. In that case, your x is equal to half. So 1 over 1 minus x is also is going to be 1 over half, that is equal to 2. So your Tx is going to be tau times ln 2. And that is the equation that we talked about in the last page. That if you want to reach 50% of the full level of the VDD, in other words, if you want to reach VDD over 2 from 0 voltage level, then that time taken to reach there is equal to tau times ln 2, or 0.69 times tau, where tau is equal to R times C. All right. Similarly, you can figure out what would be the rise and fall times. For rise and fall times, you are interested in when x is equal to 0.1, because you're interested in 10% to 90%. So x equal to 1 to x equal to 0.1 to x equal to 0.9. So t 0.1 is going to be tau times ln 1 over 1 minus 0.1, that is ln 1 over 0.9, which will give you 0.1 tau. Similarly, if you have x equal to 0.9, if you put in the values, you'll get tau times ln 1 over 0.1, because in the denominator you have 1 over 1 minus x. So your numerator is 1, denominator should be 1 minus x. If x equal to 0.9, you have 1 over 0.1. And that will be equal to 2.3 times tau. So if you're interested in 0.1, 10% to 90% rise time, then you can define that as 2.2 times RC, which is nothing but 2.3 tau minus 0.1 tau. Similarly, you can figure out what would be your 20% to 80% rise time theoretical. So in that case, just put x equal to 0.2 and x equal to 0.8 for 20 to 80%. And during discharging, you can do the same thing, and you will end up with the same equation, that your T fall is going to be 2.2 times RC. Now in the homework question, you are asked to find out the T rise and T fall. And how do you find that out? Because you know that T rise and T fall is going to be, let's say, 2.2 times RC. But what is R and what is C, right? So if we go back to the homework question, you're asked to find out the let's say rise, fall, or the propagation time. In this case, you are asked to find out propagation times of high to low and propagation times of low to high. And that is going to be 0.69 times RC. Now the question is, you probably do not know what is your R. What is your C? The C is going to be the capacitance that is connected as load. C is the capacitance that will be connected as load. And in the question, if you see that in the question, it will be given that C is 10 picofarad. The capacitance that is connected as load is 10 picofarad. But you need to find out what is your R. And your R will depend on the on resistance of the transistor, right? So what is the on resistance of the transistor? Again, this is something we have learned before, but maybe we can just revisit that a little bit. That the equation for, remember that the transistors, when they are on, they are in triode. When we are learning about analog circuit, we always consider the saturation equation. That is current equal to K over 2 times V overdrive squared. On the other hand, if you look into the triode equation, it will be slightly different. For the triode equation, let me see if I drawing it here, or I can just derive it. Okay. So for the equation for triode, your current is going to be K over 2 times VGS minus VT times VDS okay. So minus VDS squared. So that was my current. The current ID or the drain current through a transistor is equal to K over 2 times VGS minus VT times VDS minus VDS squared. You can go back to the previous notes if you want to see how this equation was derived. Now we know that if the transistor is in deep triode, so again, we draw the same graph that we have probably drawn 1,000 times in the course, that VDS versus ID. That looks like this. For saturation, you are interested in this region. However, for triode, you are interested in this region. That is where the transistor behaves as a switch, because the drop across the transistor, which is VDS, that is the drop across the transistor, is very small when the transistor is in deep triode. And you know, for a switch, the drop across the switch should be 0, ideally, if the switch is on. If the switch is off, you have infinite impedance, and the drop across the switch should be infinitely large. So if your transistor is in deep triode, your VDS squared term, that is even smaller. So VDS is, let's say, 50 millivolt. So VDS squared is 0.05 times squared. So VDS squared goes away. So you have ID equal to K times VGS minus VT, that is equal to V overdrive, times VDS. That is equal to your ID when you are in deep triode region. So what is your on resistance of the transistor when you are in deep triode? Resistance is voltage over current, right? What is your voltage across the transistor? That is VDS. What is your current through the transistor? That is ID. So what is the R on resistance of the transistor? That is just equal to your VDS divided by ID. And what is VDS divided by ID? That is equal to 1 over K times VGS minus VT. Correct? So that's basically going to be your on resistance of the transistor. Now, if you have that, then you can find out what is going to be the on resistance of your NMOS transistor as well as the on resistance of the PMOS transistors. Let's consider the on resistance of the NMOS transistor A. And that is going to be 1 over K times VGS minus VT. What is the gate voltage? Gate voltage is A, and the transistor is on only when A is high. So the gate voltage is equal to VDD. The source voltage is connected at ground. So your VGS minus VT is going to be VDD minus VT. Okay. And if K is given, VDD is given, and threshold voltage is given, you can figure out what is the on resistance of the NMOS transistor. Similarly, if you want to find out the on resistance of the PMOS transistor, of course, it will be the same equation. And then you can find out the on resistance of the PMOS transistor is just 1 over Kp times VDD minus VTP. And then you can figure out what is the on resistance of the PMOS transistor as well. Now that you have found out the on resistance of the NMOS transistor and the on resistance of the PMOS transistor, you look into the circuit. So for example, the circuit which was here, what would be the on resistance when you are trying to, when you have the pull down network activated? If you have the pull down network activated, you have the on resistances of the NMOSs over here, right? The NMOSs will be on, these switches are on. And when the switches are on, they are not zero resistance. They have a finite non-zero resistance. And that finite non-zero resistance is something that you had figured out to be 46 ohms. For PMOS, that finite on resistance is 75 ohms. That's what you figured out here. So when your pull down network is activated, your on resistance is just going to be the series and parallel combination of whatever resistances you have. So you had A, let's go back to the circuit a little bit. So you had this A in parallel with B, and then you had D in parallel to that, you had C over here. Now in the question, it was given that find out the propagation delay, high to low propagation delay or low to high propagation delay, when your VA, VC, and VD, they are equal to digital 1, and VB is equal to a digital 0. So if your VA, VC, and VD, they are high, that means my transistor A is on, my transistor C is on, and my transistor D is on. Whereas my transistor B, that is off. Right? So that was given in the question in homework 9, that if VB is equal to 0 and VA, VC, VD, they are on, then what is going to be your high to low propagation delay or low to high propagation delay? In this case, they are interested in the high to low propagation delay because your pull down network is activated. So you have a path through these two transistors, or you have a path through this transistor. So you just create that resistive network, 46 ohms here, and 46 ohms on the right-hand side in parallel to that. So what is the overall resistance? 46 in parallel with 93, that will be about 31 ohms. Now you can calculate what is going to be your TP high to low. Why you are interested in high to low? Because you want to discharge your output from a high value to a low value through the pull down network. Right? If you talk about low to high, you have to talk about the pull up network, because pull up network pulls up the output and pull down network pulls down the output. So TP high to low is equal to 0.69 times R times C, and then you can calculate that by putting this resistance to be 31 ohms and the capacitance to be 10 picofarad. Similarly, you can find out the fall time, which is 2.2 times RC, and 2.2 times RC will be 682 picosecond. There was another part of the question where it was asked that if VA, VC, VD, and VB all are 0 volt, then what is going to be the low to high propagation delay and what is going to be the rise time? Of course, as you see that all of these are 0, so you know that the PMOSes are going to be on. That means that the output is going to be charged through this path. So VA, VC, VD, and VB, all of them are 0, which means all these transistors will come into play and all the on resistances of the transistor will come into play. Just find out what is the equivalent series parallel resistance, right? That is going to be 126 ohms in this case. So TP low to high is 869 picosecond, that is 0.69 times RC. And T rise is 2.2 times RC, which is 2.77 nanosecond. So now you see that a circuit can have unequal rise time and fall times. Maybe in your simulation, sometimes some of you might have seen that the rise time and fall time are not equal for a circuit. And that is basically because of this reason, because the on resistance of the NMOS and PMOS may not be equal. And also when they turn on and when they turn off, that is unknown, that is data dependent. And because of that, your the rise time and fall times could be very different, which is seen in this case. And your rise time and fall time will actually determine the maximum frequency that you can have for that circuit. For example, if my rise time is particular amount, let's say T rise, my signal does not even rise to VDD if I have not spent that T rise amount of time. And then you need to have a T fall, which is again some amount of time. So what would be the minimum time period for that signal is going to be T rise plus T fall. So you have to give the output to rise, time to rise, and time to fall, before which you can start the next cycle of rise and fall. So your maximum frequency will be determined by what is your T rise and T fall. So 1 over T rise plus T fall is going to be the maximum frequency that you can operate your circuit at. And that is the way to find out what is the maximum operating frequency of any digital circuit. All right, questions?
Does the right volt have a certain rule in
yes. So because now ideally you would want your rise time and fall time to be equal. So you'd like to at least design your R on N and R on P to be equal. However, when your transistor turns on or turns off, that is data dependent. So you cannot do much over there. And that is the reason why if you create a very complex network, let's say with 100 transistors in the pull down network and 100 transistors in the pull up network, there is no way you can match the rise time and fall time for every data condition. right? And that's why people try to divide. I mean, they do a divide and conquer approach, that divide it into smaller chunks, even though at the end that might cause more amount of power consumption, but at least you can get a higher frequency because it's easier to control a smaller set of transistors than hundreds of transistors at the same time. So we'll stop here, and that's the end of the semester for this course. Of course, we have the final exam, but this will help you to solve this homework number 9. I'll also post this just so that you have an idea about how to solve these homework problems. But hopefully it has been a good learning experience. And let me know if there are any questions regarding the exam or regarding anything related to the course. And I hope all of us learned something throughout this entire experience. Thank you. Yeah, thank you. Yeah, thanks, guys.
I'm gonna be sending the homework soon.
Sure. All right, no worries.